In the previous few videos, we focused on the theoretical aspect of solidification. In this and the next videos, we'll look at the practical side of solidification. We'll start by looking at casting, which is a 1,000-year-old technique. For most of today's video, we'll use the website from the University of Cambridge. The name of the website is called Dissemination of IT for the Promotion of Material Science. Do it POMS, that's how I call it. I used this website extensively when I was a graduate student, and I learned a lot from the website. I strongly recommend you to check the website out if you are a student in material science and engineering. Okay, now let's look at casting. For casting, what you do is you pour liquid metal into a mold. The molten metal solidifies in the mold. Since the mold is usually kept at room temperature, it's at a much lower temperature compared to the molten metal. You have a huge undercooling here that encourages the formation of super fine grains near the mold wall. There's also a special name for those superfine grains near the mold wall called chill zone. From the chill zone and the liquid metal or the molten metal, you'll also have the undercooling, and that encourages the formation of dendrites. And those dendrites also have a different name called columnar grains. Looking at a real example from cast aluminum, and you see that near the mold wall, you have very fine grains, and that's the chill zone. And more into the material, you get the columnar grains, which are formed by the dendrite formation. At the very center, the undercooling is not large enough, therefore you have more aqueous grains present. So what you see here is a typical as-cast microstructure. In the outmost layer, you have the chill zone superfine grains. Moving away from the chill zone into the material, the microstructure is dominated by the columnar grains, and at the very center, you can also have the aqueous grains. It is important to point out that if you change the undercooling, you can actually engineer the as-cast microstructure in ingots. On this slide, the top three schematics are the top views, and the bottom three schematics are the side views. In the example on the left, you see the chill zone and columnar zone. There is no aqueous zone. What this tells us is the casting condition has a large undercooling. The example in the middle resembles the typical as-cast microstructure. In the L side, you have the chill zone, and when you move towards the center, you have the columnar zone, and at the very center, you have the aqueous zone. For the third example, the one on the right, you only get the aqueous structure. What this tells you is the undercooling is very small. The chill zone and the dendrites are not favored during solidification. I also like to share with you one example I really liked from metal 3D printing. What you see here is the cross-section from a single track experiment. The laser only scanned on the surface once, and what you see here is the melt pool from the single track experiment. One thing that is striking to me is at the edge of the melt pool, you see those superfine grains that resembles the chill zone we see in conventional casting, and away from the chill zone into the material, you see all those columnar grains. It's like casting in the micron scale. The work was done by Dovji and the co-authors and published in Materials and Design in 2020. Next, we'll discuss some practical examples of casting. The first one I'd like to share with you is sand casting. You first make a model of the part that you want to make. The model can be made from metal or wood or any other materials. You use sand to bury half of the model to make half of the mold. Then use more sand to bury the rest of the model, and that will make the other half of the mold. You will drill some holes, and the ones called runner is the one you use to pour metal in. The risers will act as exhausts during the casting process. Open the two halves of the mold and remove the model. Close them again. Pour the molten metal in. Wait until the part solidifies and cools down. Break the mold and you will have your sand casting part. From sand casting, you can get some fairly complicated shapes and geometries, and here are some examples. The second example of casting is continuous casting. If all you need is a thin sheet, you can directly cast molten metal into sheets. I took the example from BlueScope steels in Australia. The process is called cast strip. The molten steel is poured through the casting rolls and solidifies into a thin sheet. That saves the need to do hot rolling for multiple passes, therefore can save energy and can increase the efficiency of production. The third type of casting I like to cover here is called investment casting. It is a technique heavily used in the aerospace industry. You first make a wax model, then assemble the models, dip the wax into a ceramic slurry. Heat up the parts, the ceramic slurry will solidify to form like a shell and the wax will be molten. You can pour the wax out. The ceramic shell now gives you the mold and you can pour molten metal into the mold, break the ceramic shell and you have the parts. Using investment casting, you can make really complicated shapes and geometries. For example, the turbine blades you see in jet engines, they are usually made from investment casting. Before wrapping up today's video, I'd like to introduce you one unconventional way to do solidification of metals. The process is called melt spinning. You have the molten metal injected on a high-speed spinning wheel. A ribbon will form. Because the undercooling is so huge, the metal atoms do not have enough time to form crystals. It will be in the amorphous state. This material is called metallic glass or amorphous metals. On the right, I'm showing the work done by Professor Mingwei Chen. If you do diffraction at a large area, you will see amorphous ring, telling indeed it's amorphous. However, if you keep reducing the electron beam size, you start seeing diffraction spots. What this tells us is the metallic glass, it does not have long-range order, but it has short-range order. In this video, we largely focused on casting. We also slightly touched upon metal 3D printing. In the next video, we will shift our emphasis to metal 3D printing, a popular technique enabled by solidification of metals.